with animals, for sure. Yeah, like if you ever like see like a baby bird or something and you try to help it, then it's like the mom like rejects it later because it smells human and it says like,
surprise, motherfucker.
I'm not taking you back. Okay. One sec. I need this music to go down. It's a little too loud. Okay, so a shunt resistor, Sib, is really just that's just a fancy word for in parallel. So that just means like parallel is what it means. Yeah, that one. I know we have a little r, the resistance of the galvanometer, and the r, yes. So this is I cannot spell parallel today. Jesus, I'm having a stroke. Parallel. And yeah, this thing here always is kind of just like the meter. This is the galvanometer, or I just call it like the meter. Okay. Wait one sec. I need to make sure this is working. Yeah, so the key thing is that the meter needs to take a low amount of current. Okay, so meter, this needs low current. Okay, so depending on how these things are hooked up, depends on what values you need for the other resistors. Okay, so if you're measuring the resistance of a circuit, where let's say you have just a simple battery and a resistor, and you're trying to measure what the resistance of this thing is. Let's say, for instance, you use a voltmeter. You should know that to connect a voltmeter up to this, I need to do this in parallel. Okay? And so this is going to be a voltmeter, which is the same thing as having this, what they call this, like R series, and then the galvanometer. It's the same thing as this. And then G. This small thing here, so this just means the internal resistance of the galvanometer, because the galvanometer is made out of wire, but that resistance is assumed to be really, really small anyways, so you don't really need to deal with it. What's your deadlift, bro? I don't do deadlift. Once you're over 30, you should stop doing deadlifts. They're not worth the risk. The risk is not worth the reward. You get injured way too quickly with it. Okay. So, if I have a regular circuit here, and I'm trying to measure the voltage, and then this is in parallel, right? I don't want to disturb the overall resistance of this circuit. So, hooking this up in parallel, I need this to have very high resistance. Okay? The reason for that is it's going to make sure that most of the current still flows through the circuit as normal, right? Because if this is very, very high resistance, the current does not want to go this way. Current always looks for like the easiest path. And also what that ensures is that if there is going to be a small amount of current that goes through this leg, and that means only a small amount of current is going to get to your meter, to the galvanometer, and also whatever voltage is measured here will be the same as the voltage measured here. So it's a way to measure the voltage of a device, is you put something in parallel with it. You know from parallel circuits, those legs have the same voltage, and so this allows you to measure voltage. Now let's say, for instance, you have a circuit, you're trying to measure the current. Sorry, let's move this down. So this is voltage. And then here we go. This let's use a different color. Yeah, let's use red. Let's use red for the current. So measuring current. So remember that for current, an ammeter is always put in series with the circuit you're trying to measure. How can it have the same voltage? Okay, good. Yes, it won't affect it much. Yeah. Because that's why high resistance is needed. Yeah. And so, to that effect, right? Voltage between, like, two spots. If the voltage between here and here has to be the same as the voltage between here and here, because they're the same, it's the same node, it's the same spot you're measuring potential about. Imagine, like, I don't know, something's, like, hot here and something's cold here. Well, the hot versus cold across this is the same as the hot versus cold across this, because it's the same. It's the same point. If you want to see that with, again, why that doesn't affect the circuit. Let's say this has a resistance R1 and that's R serial. You know, so usually let's just say this is just V naught. What's up, Amelia? We would just have that V0 is equal to, let's say, like I0 R1. Okay, so the amount of current being measured, I0, is just equal to V0 over R1. Cool. Now let's say we put in the voltmeter. This is a parallel circuit with this. So this has now an equivalent resistance that's equal to two resistors in parallel. So now you say, like, oh, well, R equivalent is now equal to 1 over R1 plus 1 over R serial, all to the negative 1. I'm ignoring the resistance in the galvanometer. Like, don't worry about it. It's such a small resistance, we don't really care about it. Now, if R serial is much, much greater than 1 over R1. Sorry, much greater than R1. And let me show you how that works. Because I could do math here. If I wanted to combine, I'm doing it algebraically. So in order to combine fractions, they have to have the same denominator. So this would have to be multiplied by R serial over R serial. This would have to be multiplied by R1 over R1. You would get R serial plus R1 all over R serial R1, okay, to the negative 1, which would be the same as, well, one second, I don't want to say this. I want to say something about, like, R serial is greater than R1, though. Oh, okay. One sec. This is equal to R serial R1 over R serial plus R1. Ooh, very cool. Okay. I think I see what I want to do here. And then I'm going to divide both sides by R serial. This is just showing how the math works. Watch what you get here. Yes, please do the math. The harmonic sum. Yeah, this is kind of cool. So this is going to be this over this. So the R serials are going to cancel. And so you're just going to get R1 over, and then this is going to be 1 plus R1 over R serial. Right? Because this is going to cancel this one. And then you're just going to get R1 over R serial. Well, it's just going to get, you're just going to get 1, and then it's going to be plus R1 over R serial. Okay, cool. So this is also equal to R equivalent. Just another way to write it. We're just doing, like, some fancy algebraic manipulation. So here's the cool thing. If R serial is much greater than R1, then R1 Because it's series. Yeah, it's called R serial because it's in series with the galvanometer. It's in parallel with R1 though. This is the equation for resistors in parallel. And then all I've done is I've done some math where I've made them have the same denominator. So here I did like R serial, R1, R1. And now these can add to get you this over this, but then it's to the -1, so you flip it. And then I divide the top and the bottom by R serial, and I get to here. So if R serial is much greater than R1, then R1 divided by R serial is basically equal to 0. Okay? Because this is a ratio, right? This is like saying, you know, 1 million, right, is greater than like 10. So if I do R1, which is 10, over R serial, 1 million, that's basically 0, right? Because it's like that's 100,000. Sorry, actually, it's very small. And so this is something in physics you want to get very comfortable with this. In physics, this is why math people hate us. We use a lot of approximations. We do a lot of things by what we call like significant terms, and we'll like drop things off as being insignificant. And the reason we do, yeah, evil, yeah. He's like, no, you can't do that. Pi is not 3.
What the
That's the engineers, dude. The engineers say pi is 3. That's not us, dude. That's not us. But you want to get really comfortable with getting rid of variables if things are orders of magnitude different. So if I say R serial is much bigger than R1, then R1 over R serial is 0, effectively. This is the thing that makes math people seethe. They get so mad about this. But it is a critical thing in physics. We do this so much. Because now, I can get rid of this. And I'm left with, oh, R equivalent is now the same R1. Use derivatives and limits like normal people, damn it. Yeah, we love just like it's 0, it's 0. So that's the point. So if R serial, the resistance here is much greater than R1, then the voltmeter makes the equivalent resistance the same as what it was before we hit the before we connected the voltmeter. It does not change the resistance, and because of that, it won't change the current, and it just doesn't change the circuit, which is great, but it still will measure voltage because some current will leak through here and hit the meter. It's pretty cool. Yeah, I think it's, yeah, Nick, it's super fucking wicked. I actually, honestly, I knew that ammeters had to be in series and voltmeters had to be in parallel, but it wasn't until I taught this course that I understood the exact, like, physics behind it. Like, the exact circuit analysis. I already knew, like, oh, high resistance, low resistance, but I didn't know specifically how it was doing it. But now I see it. It's actually really cool. Okay, so I mean, you still have the chance, dude. What? You're like... Nick, you were so young, dude. You still have the chance to learn it. Circuits are dope. And honestly, like, very useful if you want to get any sort of job, being like an electrician or something. Or even an electrical engineer. Really good paying jobs, too. And AI is not taking out electricians anytime soon. In what school? This would be like an electrician school. I don't know what exists for like electricians, but this would either be an electrician school or this would be a more formal electrical engineering degree, which I don't think you want to do, Nick. That's just like, it's a lot to do that. Electrician school is a trade school. Yes, it is. I mean, is there an electrician school? That's a good question, actually. Sorry, before I do this, I just want to make sure. Electrician school. Where do I go to? Yeah, here we go. Electrical Training Institute, Los Angeles Trade Tech. So like a technical college would probably do electrician stuff. And you probably need to know a little bit about circuits. I guarantee you learn about how an ammeter and an ohmmeter works. And the advantage of that is, Nick, for you, is that you don't need to know calculus to do this stuff. If you start going into like electrical engineering, then we got to start writing calculus equations for this. You just read about ammeters and voltmeters today? How awesome it even helped you. Imagine how much I'm learning. I know, you're all seeing this for the first time. I understood how ammeters and voltmeters needed to be placed. I didn't understand the physics of, like, why. Or it was just never taught to me. Until, like, I taught it to you guys. And I was like, alright, sick. Okay. So, if you have an ammeter, in this case, you want the shunt resistance to be very low. This one, we want this to have a very low resistance. Okay. Such that now most of the current does run through here. Okay. So we would say, like, it's kind of like, it's very analogous to the voltmeter. So this is like most, and then this is like less current. Because again, current's lazy. It wants to go where there's the least amount of effort, and that's going through something that's basically a wire, a low resistance. Here, right, it's kind of the same thing. Here we say, like, most of the current. Maybe we can make this like kind of small. So, most current flows as usual. And then less current flows into your meter. And the same thing happens here. So here, current decides to keep going the way it usually goes because the other path sucks. Like, it's really, really difficult, right? Here, with an ammeter, current decides to go the regular way and not through the meter. Not because it sucks here, but because it's really easy to go this way. It's kind of like the carrot and the stick. It's kind of funny here. This is kind of like the stick. Current's like, nah, dog, I don't want to go there. That has way too much resistance. So it goes the regular way, and a little bit goes to the meter. Here, it sees this as like the carrot. It's like, oh, well, this is really easy. Let me go this way, and I won't go this way because this has relatively more resistance than the regular way. In the lab, I've done electroporation, deliver nucleic acids into this. Yeah, like electrophoresis. That's another one. In any sort of biolab, you would do that. Yeah. So yeah. So if this is low resistance, right, and this is now in series with your regular circuit, right, an ammeter is in series. You know, right, that R equivalent is going to be equal to then R shunt. Or you could say like R of the ammeter. Plus, let's say, again, this was R1. Nice. Plus R1. If this is really low, this is basically 0. Your R equivalent is still the same R1 before you even put the ammeter on there. Oh, thanks for the follow, dude. Right. And then if you're looking at the resistance of your ammeter, let's say like R ammeter, that's equal to the resistance of your galvanometer, right? So that's like 1 over R plus 1 over R shunt, all to the minus 1. So again, let's kind of do the same analysis here, where I'm just going to combine them. New follow. We do love the follows. Okay, so this is R shunt plus R all over R shunt times R to the minus 1. You flip it again. That gets you R times R shunt over R plus R shunt. And then, in this case, I'm saying that R shunt is much less than R. For an R, this is R. It's like the gauge R. The galvanometer, R. The resistance of the galvanometer. Here, we'll just put a G on it for people. Okay, now watch what happens, right? If R shunt is much, much less than R galvanometer, that means that R shunt over R galvanometer is basically equal to 0, right? Because you're taking something small divided by something big, that gets you 0. So now look what happens. If I divide everything here by 1 over RG. Slayer Darth, hey Jake in chat, what's going on? Who's Jake? Who's Jake? I'm not Jake. This is R shunt, and then this is going to be over 1 plus R shunt over R this, right? Remember, this is now 0. So now you just get R shunt. So that tells you that R of the ammeter is basically R of the shunt. And if the shunt has a very low resistance and it's basically 0, then the resistance of the ammeter is basically 0. And therefore, your equivalent resistance of your circuit doesn't get modified too much. Yeah, who's Jake? Anyways, yeah. That's how that works. Geo, you're Jake now. Cool. Yeah, the more I teach this, the more I understand it more and more, and I think it's really cool. I think ammeters... I didn't know ammeters and ohmmeters were so cool. Never said my government name, dude. What do you kids call it? Your dead name or something? Your previous name or something? I don't know. All sorts of wacky shit going on. Funny names. Oh, dead name is for transgenders? Oh, oops. I can't say that then. Someone's gonna get mad at me. Okay. Alright, cool. Sip, I hope that makes sense. Burner name. I like that. Yeah, I do have a burner name. Yeah, for sure. Yeah, playa name. Yeah. Oh, interesting. You're talking like burner phone. Yeah. There's another thing in the Burning Man community where you have a name and it's called your playa name. Because playa is like the name of where Burning Man is. It's called like, it's funny, it's like the beach, but it's middle of the desert. So, but you're all, there are rules at Burning Man about like your name, your playa name. And it's that it can't be, you can't come up with your own name. It has to be given to you or gifted to you from someone else. So somebody else comes up with a name for you and they give it to you, and then like it's their gift. It's kind of funny. Yes, HH. Let me help out one of the students in my UCLA class, Josh, who's been waiting. I gotta do. Let me go through one of his. I think he's got 2 homework questions first, and then yeah, I'm down to do some Ampere's law. Let me see. Which one did Josh need help with? 11 and 15 on the circuits homework. Yeah. Okay. Let's go find it. What if it's like penis? Some of them are, dude. Some of the names are like kind of weird. And yeah, that's your name then. You can always change it if you don't like it. Yeah, you don't have to accept it. That is the rule at Burning Man. You don't have to accept the name given to you, but you can't choose it for yourself. Like you have to accept someone else giving you a name. I think someone gave me the name Dorado, which is like gold in Spanish. So I took it. I was like, cool, I'll take Dorado. And it changes like every year. Like, I gifted some names to people. One of the names I gifted was, like, Dr. Bluebug to one of my friends. Because I was like, you're Dr. Bluebug. It was just kind of funny. Just wacky stuff. Yeah. It just comes up. You're just, like, spur of the moment. You're like, here's your name. Reki, I will do yours in a bit. One sec. I'm helping out UCLA stuff first. 11. Ooh, that is a weird one, Josh. And then 15. I did 15 during office hours yesterday. It's a lengthy one. Yeah, I'll do 11 for you, Josh, but I'm going to point you to office hours for 15. I'm going to point you to yesterday's office hours for 15. because that one is pretty lengthy. Why blue bug? I don't know. It just kind of like came to me or whatnot. I just felt it. Oh, 11. Actually, I did 11 as well, actually. I've done all these questions. Oh, okay. Yeah, this was done during another office hours. Fuck. I didn't save the whiteboard for this one, did I? Okay. I'll do 11 again. But 15. Yeah. That was yesterday. But 11, I'll do it again. Because maybe I probably need some more interpretation of this, honestly. Actually, let me get the big image version of it. Just go through the VOD. Yeah, I agree. That's actually the one thing I do like about teaching online, is that it's very easy because everything's recorded. Everything is posted somewhere. I can always tell someone, hey, just like go check this out. But when I teach in person and I have office hours in my office, it's not really being recorded, or maybe I should record it. So it would get kind of annoying that I would have like a student come in and ask a question. I'm like, cool, here, we did it. And then another student would come in late and ask the exact same question. And I'd be like, oh man, like we got to redo it all over again. VOD is video on demand. That's what it stands for. Okay. So, in this one, the good thing to, let's think how I wanted to analyze this. Yes, I remember how I want to analyze this. I do this. I always draw stuff like this, man. And I draw like kind of like a direction of current. Okay. And then this is the negative end, which is always going to have current coming back. Okay. Okay. So then there's kind of like some questions about like what's happening here. Yeah, this is like the mess. Okay. So first off, I know I can make D and E as resistors in series because they're literally right next to each other, right? You see how the end here, they're right next to each other. It looks like it goes all in this in the question is like where the current goes here. I'm pretty sure what happens is I want to say it goes like this and then this like comes back into here. But we got to see first. Okay. So D and E are in series. So you have RDE is equal to RD plus RE. And that's going to be equal to 12, right? Based on this. It's 12 ohms. Okay. So now redraw our picture. Grab this. So now I'm not gonna, this is gone. What's up, Monkey Man? And we have now replaced this with a new resistor. RDE. Okay. Notice that RDE and RC and RB are all in parallel. It does sometimes, Nick, so we'll see. So all three of these things are in parallel because the top ends of all of them meet at the same point, right? Okay. This all meets with this, meets with this, meets with this. And then the bottom ends all meet with each other. Yes, you're right, Nick. That can happen. That's like competing currents. Yeah. So this is going to be called RBCDE. Wait, is that the symbol for resistor? Is that the same thing as rectangle? They do mean different thing. Oh, I see. No. You're referring to like this. Yeah, I believe this is also resistor. But this is kind of the more accepted version, I think. So RBCDE, BCDE, that's equal to 1 over RB plus 1 over RC plus 1 over RDE, all to the minus 1. Which, B is 4, C is 6. So that's 1/4 plus 1/6 plus 1/12. So that's going to be 3/12, 2/12. So that's 6/12 to the negative 1. So that's going to be equal to 2. Cool. Okay. So now, rheostat's this. This is a rheostat. Variable resistor, yeah. All right, so now we're gonna get rid of all this. This all goes away. And instead what we have is just a new resistor here, which is going to be RBCDE. So all of these things like collapsed into each other, kind of like an accordion, and just became a single resistor here. So now this is RBCDE. Okay, now this is pretty cool. You should be able to see like kind of how current's running here, right? Because current's going to go this way. And then from here, right? Current's still... Here, let me do like the in-betweens, right? Current from here still wants to go this way. So that's this way. So that's this way. And actually, sorry. Let me make this the light blue one. So that's this. Where here, current is moving this way, which means it's going to move that way, and it's going to move that way. Now everything looks consistent, right? See how, like, current is starting here. It's moving this way, and then it's splitting between these two. Well, here's the cool thing, right? Now RBCDE and RF are in series because they're close to each other. Yes. Yes, great, Nick. You're getting it. You see it, man. Yeah, that's great. Yeah, exactly. So now this right here becomes RBCDEF, or yeah, we could say FBCDEF or whatever. FBCDE. That works as well. So that's equal to RBCDE plus RF. So that's going to be 2 plus 14. So that's going to be 16. Okay, very cool. So now, again, let me erase some stuff. This is going to go away. And this is just going to be... Oh, and this is also going to be gone, right? So let's see if you can see the next thing, right? So now... Here, let me copy all these. Yes, because they all go through F, yeah. You can also say, that's called in series. Nick, because they like follow each other in a line. It's like it's called serial. It's like, yeah, straight through a line. Okay, so now you have this and this, but look, these two things are now in parallel. I'm running out of colors. All right, we're gonna use brown. Yeah, so now since these two things have the same starting point and the same ending point, these are in parallel. And so this is going to be R F B C D E F B C D E G, which is going to be 1 over RG plus 1 over R F B C D E, all to the minus 1. Resistance G is 16. Okay, so that's 1 over 16 plus... Oh, 2 plus 14 is not 6. It is 16. Oh, nice. Plus 1 over 16. This actually comes out to be really nice. So that's going to equal 2 over 16 to the negative 1, which is 16 over 2. So this is going to equal 8. Nice. Okay, cool. So now, what do we got? So now this is all gone. This is gone. This whole thing is gone. Yes, it's F, B, C, D, E, G at the vertex, right? And then this is just a simple circuit. So now this is gone. Yeah, this is no longer here. Actually, here, let's just erase this whole thing. Let me get rid of this. Or no, this was a brown color. Now this is R, F, B, C, D, E, G, which is just equal to 8. And now these two are in series. And so this is just R, A, B, A, F, B, C, D, E, G, F, B, C, D, E, G is equal to RA plus 8. No, it's not stupid questions. No, it's great. I'm glad you're following along with this, Nick. Really cool. Let me make this. This is actually a really cool diagram I made for this one. One of my better artistic pieces, I feel like. So RA is 11.5. Oh, fuck. So this equals to 11.5 plus 8, which is equal to 19.5 ohms. And then the question's asking for the single equivalent. Yeah, so it should be just 19.5. Nice. That's how you do that one. Yes, art is becoming better. This is really cool, like how we did this. Nice. Okay. Josh, does that make sense to you? Yeah? Hopefully? Yeah? I think it's cool. Sonny, what's up, Sonny? I think my chat might have lagged out on YouTube. Took me a minute to realize those resistors are in parallel. It works out very well in the end. It really does, yeah. Very cool. Dr. G, Dr. Goat. I love that, dude. Dorado's like golden, Oro is gold. Yeah. You can't unmute? Oh, okay. Well, that's on your side, Sonny. Homework SU22 answer key. What's this? Ooh, convert using SI units. That's pretty cool, Sonny. What's this for? I see it. Could you work through problem 1? Sure. Yeah, you know what's difficult about this one, Amelia? And here, let me share the screen on Discord so you can see Sonny. Sorry. Let me know if you can see that. Let me change it to 720p. Might work better. I'll stream on Discord. See if you can see it on Discord. I cut it because I was having bandwidth things. Yeah, okay. Okay, you should be able to see it, yeah. Okay, cool. Where did you get the 8 at the end? So the 8 came from this. So we know this whole thing here is 8. And then we added that to RA, which was 11.5. Because that was given all the way up here, Nick. Said, oh, RA is 11.5. This came from us putting this one and this one in parallel with each other. Which was 1/16 plus 1/16, and then inverted, which is 8. Okay, let me see. Convert to SI units. Ooh. What is this? Wait, what is this? Pound meters? Oh, in mass? Is that what it is? Yeah, sort of math at last. Bro, this is fun. You don't like this? This is kind of mathy. Jeff's like, bring back the math, man. Oh, I don't need that. Electricity is too shocking. Wow, dude. That's a good one. The electricity is too shocking. It makes sense to me, but on Kudu it says the answer is 36 ohms. Oh. Really? Answer should be... One sec, Josh, sorry. Answer should have been RA plus 8. It should be 19.5. I don't think it's 36. No way. One sec. I'll go through and look. Oh, Josh. Your answer will be different than mine because it depends on what RA is. So here, for my question here, RA was 11.5, but the answer is 8 plus whatever RA is. So this number here is random. Okay. So whatever your number is here, plus 8. I'm guessing your RA was 28. That's probably why. Okay, just problems A to C. Let's do it. Here, let me help that out. And then Amelia, yes, I'll do question 8 from the EMF homework. Okay, so let's see first. Convert to SI units. Is SI... what is SI unit? Is that meters and stuff? Or is that's imperial or something, right? Oh, one sec, what are SI? Yeah, meter, kilometer. Okay, cool, awesome. Metric system. Okay. I don't know what the tables are that you have, but I can kind of do my own things. So I think acres has a conversion to square miles. So acres is a unit of area. So I'm going to want to know meters squared equal to 640 acres. Yeah. So let me go with like square miles. I think that's like 1 acre. I think 1 acre is defined by square miles. Well, that's in square feet. Oh, that's actually really bad. What? Oh, man. Square miles and acres? 640 acres is 1 square mile. I think this is probably the thing that you have on yours. Oh. Oh, wait a minute. What? Oh, okay. That's actually... Well, watch this. Okay, so the conversion is 640 acres is equal to 1... Yeah, different values. Yeah, 1 mile squared. Right, yeah. And then what we do here is that 1 mile is 5,280 feet, or you could use the kilometers. Yeah, 1 mile is equal to 1... I would say this, it's 1609 meters. But you have to convert two instances of miles. This is miles squared, so you need to do it again. You see how like miles times miles, this will get you miles squared, and then miles squared will cancel with this. And then also, you'll have meters and meters, which will get you meters squared. Okay? So then you do the conversion. This cancels with this. This cancels with this. So 640 over 640, right? That also just cancels. So it's just 1609 squared. Meters squared, which we can pull a calculator for that real quick, Sonny. So that's 258,881. 258,881 square meters. But how many football fields is it? Ooh, that's a good question. Look up hectares. It's a waste time. And yes, you could also say in kilometers squared. I think for SI units, though, I think it's meters. Well, this also depends whether you're using, like, what is it, CGS or KGS or something. Yeah. Okay. So then for miles, right? Yeah. I assume, again, they want meters. Is equal to 34,069 miles. Same conversion here. 1 mile is 1609 meters. And so you just multiply it, right? So 34,069 times 1609. Give me a really big number. 548, 170, 21 meters. Let's see on your solutions manual. You had a solutions manual you showed me. So yeah, they did meters squared here. Mega miles. That's interesting. I wouldn't do mega miles usually. That's a kind of a weird unit to use. Just in regular engineering, we don't really say mega miles. If anything, you could convert this to scientific notation, right? So this is 1, 2, 3, 4, 5, 6, 7. So you'd say 5.48 times 10 to the 7 meters. That's the way I would really do it, right? And then this is, right? If you move the decimal over 7 places, then you have a times 10 to the 7 in the top. It is technically a valid unit, but yeah, it is almost never used. And then that's the same thing for this one. Again, this is kind of ugly. So you go 1, 2, 3, 4, 5. And so that's 2.58, or 59, I guess, times 10 to the 5 meters squared. Yeah, petameters. Yeah. Okay, gallons. Ooh, this is an interesting one. The unit for, I think, is liters, right? So I don't know how many liters is equal to 9405 gallons. I think there's a simple conversion for this. Is it 3.8 liters to a gallon? Yes, or cubic meters, correct. Yeah, that's a weird one. It's 1 cubic decimeter. The better one is that 1 milliliter is 1 cc, 1 cubic centimeter. That's the real one we like to use. Leader, I hardly know her. Yeah, I don't know. I think this is one you can just kind of like use. Sorry. Let me bring my footpad up. Yeah. So, gallons. Yes, exactly. Yeah. I could do it the hard way. Yeah, it is. It's around 3.8, 3.79. Okay. So you can say that 1 gallon is 3.79 liters. I remember it was like 3.8. Here's my calculator. What's that YouTuber that says I hardly know her? That's kind of an old school meme, probably from further back than the internet, I would assume. So 35644. 645 liters, which again, convert to scientific notation: 1, 2, 3, 4, 3.56 times 10 to the 4th liters. Just make your teacher happy. Does that make sense, Sonny? For the conversions, the exact way you do them, yeah, will refer to what tables you're given. Because sometimes they won't give you gallons to liters. They could give you gallons to ounces to cups, and then ounces to, what is that? Milliliters and milliliters to liters. Yeah, it's yeah. But I tried to do it, I think, with like my favorite YouTuber, Rodney Dangerfield. This one also be in cubic meters. Yeah, I guess so. I don't know. To me, it's like, it's kind of like, it's a liquidy volume though. Okay, nice, good. I'm glad that made sense to you, Ollie. You get a bond coin, by the way, for asking questions in our Discord. I don't know how you found us, or if you're new, but you get points for asking questions. Okay, I think Amelia said question 8 from the EMF homework. Let me go find question 8. Oh, it's a liquidy volume. Yeah, dude, like, it's a volume of liquids, bro. So not the circuits, not the DC circuits homework, Amelia, right? The EMF homework. As opposed to a bushel. You're very welcome, Sonny. Question 8 from EMF. Question 8. Ooh, yeah, okay. This has to do with vector form of things, okay? I technically did this in office hours last week, but I'll do it again. So, current density, J, I believe is equal to sigma E, which is equal to, you're okay. So it's 1 over the resistivity times the electric field. Okay. So you just need to determine what the electric field is to due to 2-point charges. So I have a sphere with radius A. And here, I'm going to make a, well, yeah, okay. You don't like this question? This one's not bad. Why students probably don't like this one is because it's pretty heavy in the vector calculus land. or the vector math land of things. Yeah. And then this is like vector B. This is charge B, right? Okay. Yeah, the other thing they kind of messed up here is you need to you need to describe. Oh, okay. And okay. A, B, and then D is the vector connecting the two. So this right here is vector. This is a vector actually. This is vector D. Let me not put arrows on these because otherwise you're gonna think they're vectors. They're not. This is just like an amount. Here we could do like something like that. Whatever. Okay. The key thing that's kind of like left out here is that R is measured. I guess maybe R can be measured from anywhere. No, I think R is measured from A in order for this to work. Okay. So let's recall that electric field in its simplest form, right, is equal to K for a point charge. This is for a point charge. Is equal to KQ over R squared, and that the electric field points in the R hat direction, right? So if you have a point charge here, the electric field points outwards, assuming Q is positive, in what's called the R hat direction, which is just in spherical coordinates pointing outwards in the radius, right? Okay. Another way to write R hat, so R hat is a unit vector. So R hat, this is a unit vector of length 1. You can also say that, for instance, R vector with like the complete thing, that's equal to the magnitude of R times R hat. So this is magnitude of R, and then this is the direction, which is a unit vector direction, so it doesn't affect the length, right? But this is the full length and direction. Okay. So knowing that, you can also say that R hat is the same thing as R vector divided by the magnitude of R. That's kind of the key thing here as well. We don't write it when we write this equation, but this is really the magnitude of R squared. Okay. Or I think it's this. I think it's magnitude of R squared. Just make R positive. You can't have negative radii. Okay. So because of that, okay, because of this fact here, you can now substitute that in for here. And you get that E is now equal to KQ. And now this is going to be absolute value of R to the third R vector. This is another way to write this. This is like the same. It's the same. So you can either write it as 1 over R squared R hat, or you can write it as 1 over R cubed R vector. Vector includes the magnitude. R hat just includes the direction. Does that make sense so far there, Amelia? Yeah. So, looking at this, first of all, I know if I'm going to be, electric fields, I need it to be r vector over r magnitude cubed. So, like, right away, can't be this one, right? Can't be this one because they're all different, right? Can't be this one. By inspection, you could just say it's this one, right? Because this is r vector, r cubed, some vector. But let's explain, like, where this comes from. So remember that electric field is defined, this r is the distance from the point charge. This is distance from the point charge. So, if I'm measuring things, let's say I'm measuring my electric field from position A here. Let's make my coordinate system. Let's say I'm measuring my electric field here, right? And this is going to be my r vector, okay? When I'm calculating the electric field due to charge A here, which is positive Q, that's just going to be this, right? 1 over 4 pi epsilon naught, that's K, Q, and then it's going to be r vector r cubed. That's the electric field due to this, located at a distance r vector away from A. However, there is also electric field being generated from this. And that electric field is negative, right? It's a negative Q. But let's just pretend it's just Q for now, okay? And if I wanted to measure out the electric field due to this charge, I would then have to build out this vector. Sorry, let me move this B over. Okay. And I want to describe. So this right here is like RB. But I want to describe that RB down here in terms of this and this. I want to in terms of the vector from my origin at A to where I'm measuring the potential, and as well as this vector D that describes where charge B is in relation to charge A. What you should notice here is that R vector from like vector addition and stuff. Wow, thank you, Zeb. Look, there you go. There's your Prime notification.
Good job.
Professor Rossi, what's up, dude? This is equal to this vector plus this vector. Your cloud has been acknowledged. Yes, good job.
My man.
Okay, so this vector RB, in terms of R and D, is now equal to R vector minus D. Okay. Holy Doctor 900 nanograms per deciliter is cooking right now. Dude, what? Okay. So then the E field due to B is equal to KQ, we would say RB cubed RB vector. But that's the same thing as KQ. RB is now R vector minus D vector over R minus D cubed. And then the last thing you have to remember is that this is negative because we said that charge the B sphere has minus Q on it. So that's going to flip the sign of this, right? Because A minus B is the same thing as negative B minus A. And so you're going to get K, Q, D vector minus R vector over R minus D cubed. Okay. And that's why this right here is D minus R, 1 over r minus d cubed. Does that make sense? Yeah, they left some information out here. Should say that r vector is measured from A. Yeah, that makes a lot more sense. Nice. Awesome. I'm going to actually go in and edit that question. The question needs to be edited. Well done. Well done. Here, you have to say, assume, R is measured from the sphere with radius A. Maybe it's not needed. I wonder if it's not. I think I think it is. You still need to know where charge A is. Because if, for instance, you were measuring, let's say you're measuring the current density from way over here, right? Well, now this is not equal to this, yeah. You think something that's like might pop out on a test? Sorry to ask. I mean, maybe. It seems to be a common problem that people have problems with. So maybe I would. Whenever you ask that question in office hours and I look back at the recording, I'm like, thank you, Sibley. Sibley's doing the class some favors. Anyways. Yeah, nice. Cool question. Okay. You're all welcome. Let me see if Recky's still around. Let me do some of the other, a little bit more, I say boring questions that are being asked. Let's hear it. Let's do yours, Recky. It's me, Mario. What is copy pasting here, dude? What? It's me, Recky. Okay, here we go. Jeff's gonna be so happy we're doing math again. Jeff, are you happy, man? We're doing math. Look, it's math. It's also getting hot in my studio right now. Okay. What are the degree, type, leading coefficient, and constant term of each polynomial function? So degree refers to the highest exponent. Okay. So in that case, what's the degree of this one, Recky? What's the degree of A? Zev, how do you have the hype train emoji next to you? What hype train were you in recently? Or is that during the hype train we had? You did like kick off a hype train at one point on my server. Yeah, the degree here is 1. Yeah, good. Yes. So degree is 1, right? Because the highest exponent is x to the 1. Here degree is 2, degree is 4, degree is 3, degree is 5. What's the degree on this last one? The degree here is 0. Because this is the same thing as x to the 0. X to the 0 is the same thing as 1. Any number to the 0 power besides 0 is just equal to 1. So this is the 0th degree. Bro, this is easy. I know, Shantrix. Are you telling me that your brother should be asking harder questions? He's somehow getting this wrong, though. Type. That has to do with degree. So, what is type 0? Is that just constant? 0, is that a constant function? 1 is linear. 2 is quadratic. 3 is cubic. 4 is quartic or tetric. I forget which number you use. Tertiary. And then 5 is quintic. Yeah. Leading coefficient. So, leading coefficient. That's equal to the number on the highest term. On the highest exponent term. So in this case, this would be -1. This would be 9. This would be 3. This gets kind of confusing. Some people start saying the leading coefficient is 4 because it is first, but it's actually -3 because you look at what number's on the highest exponent. This is -2, and then this is -6. Okay. The constant term, that's just whatever, I guess, is not having an exponent on it. So constant term would be 3. So 3, 0, 1, 4, 9, -6. Nice. Cool. You're welcome, dude. You're welcome, dude. Okay. Equity, are you around? I see you dropped a question about 20 minutes ago. Sir Bob Ross's. He's asking about vectors, it looks like, actually. I'll pull that in, and then I'll pull yours in, HHH. You had a good one as well. I assume this is yours. Bro, your teacher needs to chill out, dog, on the caps, bro. What's with all these caps? Alright, equity, here. Let me do equities real quick. It'll take like 2 seconds. Okay. These are vectors with components. This is like component form of a vector. So, do we remember what vectors are, equity? For the class that hasn't seen before. So let's say, for instance, I'm going to do it like this. Yeah, let's say this is 30 degrees, and this is, I don't know, like 6. You can write out going from here to here in what's called like magnitude direction form. So this would be 6, 30 degrees. Or you can write it out in terms of components, which would be, oh, well, it must go a certain amount in the x direction. So that would be 6 cosine of 30 degrees. And then it must go a certain amount up in the y direction. So it would be 6 sine of 30 degrees. The other way to write this is with unit vectors. So what we say is that I hat is the same thing as going 1 unit to the right in the x direction. And then j hat is the same thing as going 1 unit up in the y direction. Okay? And so if I had a bunch of I hats, that would describe me going a lot to the right. Yeah. So, yeah, the other way to write this is you can say, okay, this is the same thing as 6 cosine 30 degrees I hat plus 6 sine 30 degrees j hat. So a bunch of different ways to write out how I go from here to here. You can either say length, direction. You can write it in component form like this, which is like bracket form. Or then you can write it in like unit vector form. Because each I hat here is just like, this is like 1 unit in the x direction. They would say like the x hat direction. And then this is 1 unit in the y hat direction. Good. Yes. So this means vector. Also, this like arrow on top, this defines vector. This is for magnitude plus direction. So you use parentheses for magnitude direction, and then you use brackets to signify it's a vector. Yeah. There are just some rules to math. Okay. So now if you have 2 vectors here and you want to add them together, it turns out you just have to add the components up together to get your final vector. So how this kind of makes sense is, let's say we have a vector here, vector A, that, I don't know, has a component here that's 3, and then another component this way, which is at 4. Let's say this is vector A. And then we add another vector to it, vector B. Let's say vector B points in this direction. Anytime you add vectors, you take whatever is like the start from this and you add it to the end of your other vector. So vector B being here is the same thing as dragging it and having it here. So here, kind of like, this is also vector B. Vectors don't really care like where they start. They're just like, they start somewhere and they go in a direction for a certain amount of space. So then this vector, vector C, is equal to vector A plus vector B. This is called the resultant vector. Now let's say vector B had some components. Say vector B went, I don't know, like minus 1 in this direction. And then like plus 2 in this direction. Well, actually, it looks like the same of it. Sorry to say. Say it's like plus 4. And then, yeah, let's actually make this. Let's make this kind of to scale. A little bit to scale. There we go. Putting this vector and then adding this vector is the same thing as adding this component to this component. See how here you went 3 to the right? But then with the blue vector, you went 2 to the left. So your resultant vector, which is A plus B, which is C, is going to have components of 3 to the right and minus 2 to the left. So this will be, we would call this like, for instance, like CX would be equal to this. This is the X component of C. And then the Y component of C is going to be the same thing as adding the 4 up from the A and the 4 up from the B. And this is going to be what we would call like CY. So from here, you can see that, oh, in the X component for C, I'm going to have plus 3 minus 2. That's the same thing as just 1. And in the Y component, I'm going to have up 4, so that's going to be 8. This can also be written as 1 I hat plus 8 J hat. Does that make sense so far, Equity? How are we doing this? I'm giving you like a real crash course on vectors. Okay. So you can extend that structure and format into doing even more higher dimensional vectors. So these are 3D vectors, because this is I hat, j hat, k hat, which means there's also a z direction. It's in 3D. Okay? But it's the same thing, right? So in this case, when we did this, right, this was the same as, what was it, 3, 4, plus -2, 4. And notice how we just like grouped the numbers, and this gave us 1, 8 as vector C. So this was like vector A. This was vector B. And this is vector C. Okay. So what I'm doing here for higher dimensions, okay, all I have to do is match them up. Okay, so this plus this will give me A plus B, but it'll give me the I hat component. This will give me A plus B in the J hat component. And then this plus this will give me A plus B in the K hat component. They're asking for just the K hat component, so I only need to deal with these two. So the K hat component would be equal to 0.852 plus 1.92, which you can pull out a calculator. I'll do it real quick. 852 plus 1.92. Nice. 2.772. And that's your final answer. Nice.
Well done! Well done!
Okay, nice. Good stuff. HHH, you want me to do this one? This one actually, dude, what is with your teacher with the all caps dog? The all caps needs to chill. Okay, let's see this one. This is kind of also gold. When are you going to announce the Kudu challenge? Tomorrow. I'll announce it tomorrow. Sorry, I still got to finish writing the final exam for these students. So I've been like, kind of like super busy, but that's done on Friday. And honestly, it's really, the exam has to be done by Thursday because I have to get my TA to review it. So Thursday I will have time to announce all the Kudu stuff. We're gonna play some Fortnite this weekend too, so be ready for that. That'll be fun. A steady current flows along a long solenoid of n turns per unit length and radius a. That's okay. It's okay if you don't know them. It's physics. It's new stuff. Derive the magnetic fields inside the solenoid. Be explicit. And show the expansion of the line integrals on the left-hand side of Ampere's law. And state why many go to 0. Okay. What's Ampere's law again? Is that the B.dl is mu naught I? Oh, it is. Yeah, okay, cool. Line integral. Yeah, okay, well, here's like a... And if y'all are watching from my 1B class, this is what you're going to have to do in 1C. Mm-hmm. Gauss's law of magnetism. It is. Yeah, it really is, honestly. It's a cool way to put it. Dr. L, good to see you, man. Tears. Yeah, so Ampere's law says that as you go around something containing current, the vector B of your magnetic field integrated along the line that happens has to be equal to mu naught times the current enclosed. So if you have a solenoid, let me get like just a graph of a solenoid. It must be easier if I just do that. Solenoid diagram, and it's probably gonna, yeah, I need something like this. Oh, cool. I actually really like this. This is great. There you go. Okay, this is a solenoid. Yes. If you look at like each individual coil, right? You have a current, which looks like this. This is like this part of the wire. And that's creating a B field that points like into the page. All right. So, and then they say n turns per unit length, radius A. Cool. Show the expansion of line integrals on the left-hand side of Ampere's law. Explain why many go to zero. Why did many go to zero? I don't think many go to zero. What? False. Where do the many go to zero? Yeah. Okay. So like for a single loop, right? You're gonna have a B field pointing inwards. And that happens over a certain like radius too. Oh, okay. Yeah, okay, cool. So B at the center of like a single loop. You have B times 2 pi A, because that's the radius of the line integral. It's also the radius of the solenoid. Has to be equal to mu naught over mu naught I enclosed. Oh, then here's a good question. I think you also multiply this by 2 pi r. Right? Yeah, watch this. Yeah, we say like magnetic field due to coil. Due to ring of current. Well, this is the crazy way. This is doing it in 3 dimensions, but we can just say it like the center. Yeah. Amelia, this is what I talk about with 1C. This is the Biot-Savart law. You have to start using cross products in order to figure out magnetic field. Let me just say like the rings are at the center. Where's just like a very easy version of this, or what? Chill. Or I guess you could do it from here. Dude, they need to fix hyperphysics needs to fix their SSH or whatever. Oh, it's mu naught I over 2r. Oh, I see. They want you to use Biot-Savart. I'll be going to your office hours for 1C. Yeah, you can. I'll be here. Oh, wow. You gotta integrate DB? Interesting. Okay. That's not Ampere's law, though. Or maybe they're doing this. They might be doing... No, it still makes the same thing. Yeah. I'll have to see how this is. But anyways, that would be just for a single finger current, but then you have to multiply this by 2 pi r because you have... This is like dB. So B is equal to mu naught I over 2 pi A. But then I think it's like times 2 pi times A. So is it just mu naught? What does it simplify to? Where's the simplification? If Z is 0... This is 1C. This is 1C. Yeah, someone was asking about a 1C question. Where's just a very simple explanation for this? There we go. Okay, this is what it is. So if Z is equal to 0, I just have mu naught I over 2. Ooh. Where's the over 2 come from? Okay. Yeah, you can't really use Ampere's law for this. You have to use B sub R. Okay, this is mu naught I over 2A. And then you have n amount of those. And then it's times n. Let me see if there's a good explanation for this. One sec. B equals mu naught n times I. Yes, show me. Show me why. This is the way I wanted to do it. I wanted to do it this way. Oh. Oh, very cool. Okay, I remember this, yeah. They didn't have LEDs when I went through it? Oh, no. Yeah, okay, here's what they do. They take a cross section, so they slice. This is why I'm not teaching 1C right now. If I was teaching 1C, I'd have to go review this. They take like a slice through here. Yeah, they take this and they slice through this way. So you're kind of looking at this. So you have like current coming up and you have current going down. Oh, I see how they're doing this. Okay, this is kind of cool. This is kind of cool. Yes, okay. And then the magnetic field you assume is just like running in one direction. So B dot DL from the sections from A to B and from C to D, this is 0. Because DL in this case is up and down, but your B field is left-right. And then, do you assume there's no magnetic field outside? AB and CD are 0 because they're perpendicular, yes. The integral of BC is 0 because the magnetic field is 0 just outside the solenoid. Yeah, but why? Why is it just given? Mm-hmm. Okay. And then, yeah, I enclosed is equal to the n times the length. But then if n is like loops per unit length, it's like n. Yeah, this is it. Big N is equal to NL. Then you just get mu naught n times I. It is. Yeah, it is. It is, Dr. L. Yeah, it is. Oh, and then we have like toroids. Oh, wow. This is cool. Yeah, these are all cool questions. Yeah. This, again, if you're watching this from my 1B class, that's what you have to deal with in 1C is magnetism. And honestly, I would have rathered that they put the electrostatics and the magnetism in one course. Like the E and the M from E and M in one course, because we wouldn't have done waves and we wouldn't have done fluids. We would have shoved that off for 1C. Because then I feel like we've already got you in the groove of doing like surface integrals, line integrals with electrostatics. So applying it to magnetics isn't like that much stranger. This is also why it's good to take 1C right after 1B. Because otherwise you got this break and you're like, oh, I have to go relearn or re-remember, I guess, how line integrals work. Okay. That's cool. Okay. I gotta go teach another student pretty soon here. We've gone on for an hour 45, a little bit shorter than normal, but it's all good. Okay, let me close out the stream. All right, thank you everyone for coming office hours. Appreciate all the questions. Ooh, we got one last minute question from Sib. What's it? Oh, Dr. G, really quick. For midterm 1, for question 10, can you clarify why the height was not 1 centimeter for part B? Let me do it for you. It's okay. I'll get you. One sec. Exam 1. Let me fix that. Exam 1. For question 10. No, you're okay. Part B. A small hole is poked in the wall of the center 2 centimeters below the bottom of the cube. So that's 2 centimeters below this. The height should be 1 then. But when you're doing, if you're trying to do like Torricelli's law here, you count the amount of height of liquid above where your hole is. So if the height here is 1, then you technically have a minus 1 amount of density 2 above you. So the height is not 1. For calculating the amount of liquid above you for the pressure. You're right that H is equal to 1 for the rho GH term, but when you're doing Bernoulli's law for the first part, which is like the P term, you have to do P atmosphere plus the height of one sec. Let me find the solutions for this because sorry, I need to explain it to you. This is in this. Okay, so we said that there's a hole poked 1 centimeter below, or 2 centimeters below this. Okay, so the hole is right here. This is where all like the water's like falling out, which I guess is the blue water. Okay. Oh, Nick. Yeah. Nick, yeah, stay around. I'll help you out real quick. Yeah, I'll do a couple with you. I have to run pretty quick here, so stay here. I totally forgot about you, Nick. Sorry. You have to remind me. Okay, this is 1 centimeter. So when you do Bernoulli's law here, right? Remember, it's like P plus 1/2 rho V1 squared plus rho 1 G. H is equal to P plus 1/2 rho V2 squared plus rho 2 G. And that's in like the two situations. So outside, you have atmospheric pressure. You're going to have some velocity, 1/2 rho V2 squared. And also, this thing falling out is density 2, so it's technically rho 2. Sorry. So let me write this, because the 1s and 2s are confusing. Let's say this is A, and then this is B, B. Okay. So this is rho 2, because it's the second fluid that's falling out, but it's VB squared. And then this is plus rho 2 G, and then times 1 centimeter, so 0.01. Okay. I think if you just do everything in terms of, well, okay, that's happening here. If you're talking about like what's happening here, okay, the pressure is a couple things. So you have atmospheric pressure from up top. You have this amount of fluid also pushing down on you. So that's plus rho 1 G, and then that's C minus A. And then you also have this amount of fluid 2 pushing down on you. So that's plus rho 2 and that would be rho 2 G, and then this amount above you is A minus 1. And then also your height here is now plus rho 2 G times 1, right, equals this. Watch what happens here. This rho 2 G minus 1 cancels out with this rho 2 G 1. So these two cancel. And so what you're left with, and again, the P atmospheric cancels with this. And we assume this was negligible. There was no velocity of the water going down. So then I have just rho 1 G C minus A plus rho 2 G A is equal to 1/2 rho 2 VB squared plus rho 2 G. And this is technically 1 centimeter. I think as long as we keep everything in centimeters, maybe it'll be fine. No. This is 1 centimeter. Okay. Okay, so the G's all cancel at least. And you get rho 1 C minus A plus rho 2, and that should be A minus 1 centimeter. And then where was this Y? Sorry, the height of the hole is at Y1. Right. And this is Y. Let me make sure that was the same. I don't know why he said it was the same. 1 sec. 2 centimeters below the bottom of the cube. Yeah, that should be just 1 centimeter though. Okay. Did I put all these in centimeters too? 1 sec. Okay. And then this is equal to 1/2 rho 2 VB squared. And yeah, that should be the same answer he got here. Yeah, look, 1/2 rho 2 v squared is rho 1. Oh, sorry, I can't cancel. There is no g here. Sorry, I have to leave the g's. Rho 1g c minus a plus rho 2g a minus y, and that equals 1/2 rho 2 v squared. Yeah. Okay. That's the same. Also, how did I give your density? Did I give your densities in grams per centimeters cubed? I hope I did. That's the only way this works. No, I gave it in kilograms per meters cubed. Oh. Mm-hmm. Yeah, looking at the answer choices here, I think I need to convert that as well. Yeah, because we're dealing with meters. Oh, I did do that. I divided by 100. Okay, good. Okay. I was looking at my answer choices here. I was like, fuck, I hope I didn't screw this up. But no, I didn't. I divide by 100. Okay, good. Okay, so I did convert from centimeters to meters. Okay. All right. Sib, I know this is a mess. Does that kind of make sense? So, in this case, I don't think y1 really depended on your answers. This was always just 1 centimeter. But the key thing is that in this term, you had to consider this, which was like the fluid above. So this is like 1 above. And then you had to consider this, which was the 2 above. And then, yes, now you get the rho GH term where you're 1 centimeter up. And then outside, you don't have any fluid above you. Yes, the 2 different densities for sure. But it's on the left side. On the left side of the equation, this term here, this P total, needs to include atmospheric pressure plus the pressure of the fluids on top of you. So here, you have atmospheric pressure pushing down, but you also have pressure from this fluid and pressure from this fluid pushing down on you. That all gets incorporated into this big P term. This then refers to, again, the height from where you're measuring the pressure, which is, yes, 1 centimeter up, which is going to be the same thing here. You're also going to be 1 centimeter up. But in this case, you don't have these other 2 terms bearing down on you. You just have atmospheric pressure. Yeah. Okay. All right, Nick, come by real quick. Come by real quick, and I'll help you with a couple because I really got to go teach in like 5 minutes. Yeah, you're good. You're good. It's a good question, Sid. I was starting to doubt myself with like, let's see if Nick will come by. Otherwise, Nick, I gotta go in like 2 minutes. Okay, let me just end the stream. Okay, thanks everyone for coming by. Our next stream is going to be on Monday for office hours. So again, if you need to know when we stream, when you can get help, there's a calendar. That's the link for the calendar. I'll post it here for other people. Also, yeah, for my 1B students, if you ever have questions about your other classes going forward, just check that calendar, and I'm probably streaming, and you can come get help. Okay, let's go raid somebody before I gotta go teach more physics to more people. Let's see who's online. Sickish brain mush. Oh no. Okay. Go say hi to Moohoodles. Hope she's feeling better. Brain mush. I feel it. All right. Enjoy the rest of the weekend, rest of the week. Have an awesome time. We will see you on Monday. Peace.